के स्ट्रेंथ का क्या पता था। लाइव कनेक्शन जो भी हैं या मैसेज कर दें आवाज़ मेरी पहुंच रही है या नहीं। जो भी लाइव में जुड़ चुके हैं जरा मैसेज कर दें मेरी आवाज़ पहुंच रही है या नहीं। गुड इवनिंग। आवाज़ पहुंच रही है या नहीं, जरा मैसेज करें मेरी आवाज़ पहुंच रही है आप लोगों को। गुड इवनिंग। जो भी गुड इवनिंग बोल रहे हैं आवाज़ पहुंच रही है मेरी। मेरी आवाज़ आप लोगों तक पहुंच रही है ना। जाना नहीं जी, रुकना हमारे। कल के लाइव के लिए कुछ लड़के हमसे फ़ोन किए थे कि सर आप लाइव आएंगे कि नहीं आएंगे। तो मैं मैसेज आप लोग को डाल चुका था कि 2 तारीख को क्लासेस होगी लाइव, क्योंकि मैं थोड़ा कल बाहर चला गया था। तो कभी भी अगर ऐसा हो तो आप लोगों तक मैसेज ज़रूर पहुंच जाएगा कि आज मेरी क्लासेस होंगी या नहीं, और वो आप वो देख लेंगे उसका फॉर्मेट, फिर आपको ये क्लियर हो जाएगा कि क्लासेस होंगी या नहीं। अगर उस दिन नहीं होना होगा तो नेक्स्ट क्लास का मैं आपको ज़रूर इन्फॉर्म कर देता हूँ, जैसे मैंने कल कर दिया था आप लोग को कि 2 तारीख को क्लासेस होंगी। और टाइम ऑलवेज 8 ही होगा, क्योंकि दूसरे समय में मुझे थोड़ी दिक्कत होगी क्लास लेने में। और आज हम क्लास इनिशिएट कर रहे हैं और उम्मीद करते हैं कि आप लोग अब तक जो पढ़ाया गया आप लोगों को वो आप लोग समझ चुके होंगे या उसको और किसी बुक से सप्लीमेंट कर चुके होंगे। और नेट के लिए भी आप लोगों को मैंने किताब रेकमेंड किया था, उसमें भी ये सारी बातें हैं। मेरे क्लासेस के बाद उसको आप अगर पढ़ेंगे तो बहुत सारी चीज़ें आपको समझ में आने लगेगी, और हम उम्मीद करते हैं कि आपको कोई परेशानी उसके बाद नहीं होगी। तो आज का जो टॉपिक है हम लोगों का वो है कपल्ड रिएक्शंस। देन द टर्म कपल्ड रिएक्शन clearly represents that the two reaction systems are associated here, and the coupled reaction is one of the significant system related with the production of energy in the living world. We all know that the energy in the living system is trapped from the solar energy, or the photonic energy is converted into the chemical energy in a living system. That process, the process which is responsible for the conversion of photonic energy to chemical energy, is referred as photosynthesis. We all know very well, it is very well known phenomenon for the students or for the students as you all are. And the second one is now the chemical energy is moved from different groups of the living world in the form of food and in the form of the carbohydrate. And that chemical energy is responsible for the availability of the energy or availability of the biological energy in the other system, that is the other living system. So here, if we consider briefly here that one reaction system is the trapping of carbon dioxide in the presence of light, that is the photonic energy, and it is converted into the glucose. And the equation is very simple, that 6CO2 plus 6H2O is converted into 6 C6H12O6 plus 6O2. And here the another part, that is the chemical energy. Now the photonic energy is converted into the chemical energy in the form of the C6H12O6, and then in another system, the C6H12O6 is if oxidized, that is the in association with the oxygen, and it is converted into the CO2 and water, that is the respiration. And then the C6H12O6 plus 6O2 is converted into CO2, 6CO2 plus 6H2O. Here we observe the two systems. One system is the 6CO2 plus 6H2O converted into 6H12O6 plus 6O2. Another is the C6H12O6 plus 6O2 converted into the 6CO2 plus 6H2O. And in this system, if you remember that the change of energy in the form of the respiration, as I said in the last class, is the delta G0 is equal to minus 686 kilocalorie. And likely, if you observe in the photosynthesis, the change of energy or change of the internal energy is plus 686 kilocalorie. So the change of energy or the internal energy is in one place is represented by minus 686, and in the photosynthesis it is represented by plus 686. Here, what is the meaning of the minus and plus? Of course, it is the numerical algebraic sign. At one place it is represented by minus sign, and in one place it is represented by plus sign. That means if the sign is minus, then the energy is released in system. That means when one molecule of glucose is completely oxidized in the presence of 6 molecules of O2, it releases 686 kilocalorie energy in the system. In other way, if the 6CO2 is converted into 1 mole of glucose in the presence of 6H2O, it requires 686 kilocalorie energy. That is the internal energy. change in the internal energy. And here, the energy is coupled with the high energy phosphate bond. That means in the photosynthesis, 6 ATP, ATP is converted into the ADP, and in the respiration, the ADP is converted into the ATP. So here, one thing is significant here in the living system, that the energy is not directly involved in the workforce, but it is stored in the form of the high energy compound. That is in the form of the ATP. That is the bond energy, high energy bond in the form of the high energy phosphate bond. And in this way, when in the system 686 kilocalorie energy is stored, then it is responsible for the synthesis of 38 ATP in the oxidation of, or by the oxidation of one molecule of glucose. And in another form, if you observe the photosynthesis, then 6 CO2 plus 6 H2O is responsible for the synthesis of C6H12O6. Here I am confined only for the energetics, and so I am saying that the 18 ATP is involved in the C3 cycle of photosynthesis, and 20 ATP is utilized or involved in the C4 cycle of photosynthesis. So, in the biological system, the energy is not utilized directly in the work done, as we observed in the case of physics, or as we observed in the system associated with the physical science and chemical science. But the energy released in the system is stored in the form of the high energy bond or high energy phosphate bond, and that bond is utilized by the living system in its physiological functions or in other functions. And if we remember that the ATP is categorized in adenosine monophosphate, adenosine diphosphate, and adenosine triphosphate. We will discuss again in the next class, or tomorrow, probably tomorrow, when we will discuss the high energy compounds, high energy biochemical compounds, and probably we will discuss on the Sunday, because on Saturday I have some work. So probably, and if we will discuss on the Saturday, then I will inform you. Whatsoever, either on Saturday or Sunday, we will discuss on the high energy compounds. And here, in the ATP, in adenosine monophosphate, it is the normal bond as observed in the inorganic phosphate. And the value of the bond energy or value of the bond energy in the AMP, the first phosphate bond, is the 3 kilocalorie. In the ADP, adenosine diphosphate, one high energy bond is associated or developed or formed by the released energy of the system, and the second bond of the second bond or the first high energy bond is 8 kilocalorie. It has value of the 8 kilocalorie. And in the subsequent, in the adenosine triphosphate, that is the second high energy bond is available, and here the value of high energy bond of the second high energy bond is the 7.3 kilocalorie. In some books 8 kilocalorie is mentioned, but I am saying that the value is the 7.3 kilocalorie. And here, if we observe the coupled reactions associated with the synthesis of the high energy bond in the form of the ATP or some other high energy compounds are also available, which we will discuss, just I am saying. And here the energy released in the system and the energy stored in the system is never 100% efficient. Some energy loss is observed always. So the coupled reaction concept illustrates the principle of energy conservation and utilization in the living cell, because the energy is stored in the form of the ATP. So if the system is changed or the system is in one system, when the energy is released, it is the basic difference between the living system. So it is necessary to understand properly. Then when in the physical system energy is released, the energy is either converted into the heat or it is associated with the work done. It is the principle related with the physical systems and chemical systems. But in the biological system, the energy is released and part of the energy is stored in the form of the high energy bond, and that high energy bond is utilized later on in the living system. That is the storage. And that particular storage and release of energy or change of energy between the two systems is coupled in the living system to store the energy for the further utilization. Now, as I consider that you all understand the coupled reactions, and now we come on the free energy change in the coupled system. And here, earlier I said that the energetics is associated with the complete energetics, not by the pathway. And if we study here, there we observe that the system, two systems, both systems are coupled, and if we observe the change in the energy of the system, that the energy released and utilized in a chemical reaction, because the photosynthesis represents a chemical system, a system of the chemical reactions. Respiration also represents a system of the chemical reactions. The change of energy is 686, both in the photosynthesis and in the respiration. Of course, the sign is different. In the respiration, it is represented by minus. That means that 686 kilocalorie is released in the system, and in the photosynthesis, it is again 686, but the sign is plus, which represents that it is consumed in the energy. So here I am moving further, and I am saying that the energy released and utilized in a chemical reaction represents the differences between the energy contents of the products and reactants at constant temperature and pressure, as I said earlier. The change in the energy is released is represented in the form of the change, and that is the change of energy. And if we represented that the A is converted into B in a system, if A is converted into B, that means the change in energy, that is delta G, is equivalent to the internal energy of B, that is GB, minus the internal energy of A, that is GA. Again here we observe that a substrate and product ratio, I also discussed in my last class, that a substrate and product ratio, that means A plus B, are A and B are reactant, and after the reacting A and B, they produce C and D. That means A and B are reactants, and C and D are products. And here the ratio, if you consider the ratio of product to substrate, then it is represented by K equilibrium. K in subscript you represented EQ, that is the kinetics at equilibrium. And earlier I we discussed that the K equilibrium is D0. If you observe the change in energy of any system, that is equal to minus RT in that is log in the form of 10. In represents the log in the form of 10. It is not necessary to, it is very difficult to represent the log, but it is easy that you remember that minus RT in capital I small n in KEQ, K equilibrium. That means change in energy is equal to minus RT in K equilibrium. R is the rate of constant, T is the temperature, which I represented in my last class also. Then the DG, if you observe that it is the ratio of the product, K equilibrium is the ratio of the product divided by molar concentration of the product divided by molar concentrations of the reactants. That means the change in energy, that is D0, is equal to a standard internal energy, that is change in the standard internal energy, that is change in the internal energy is represented by delta G naught. That means the delta G is equal to delta G naught plus RT in molar concentration of product. That means in a small bracket, sorry, in big bracket, you represent C, again in big bracket, you represent D divided by, in big bracket, A, again in the big bracket, B. That is the product of the reactants and product of the products. Molar product value, molar concentration of the reactants multiplied by the molar concentration of product. And then if we neutralize these two equations, first one I am again saying, first one is dG, that is the change in the internal energy, equal to minus RT in EQ, in that is the log in the form of 10, and EQ, that is kinetics, sorry, KEQ, that is kinetics at the equilibrium. It is the first. Second is the change in the internal energy, that is the delta G, equal to change in the internal extender energy, that is delta G naught plus RT in, and product multiplication value of the molar concentration of products, that is in big bracket C multiplied by in big bracket D, it represents the molar concentration, divided by in big bracket A and again in big bracket B. And if we consider these two, then the change in the internal energy, that is delta G, equal to change in the extended internal energy, that is change in the D naught, dg naught plus RT log K equilibrium, kinetics in equilibrium. Now here, if we consider this concept, then a number of questions sometimes asked in the, particularly in the net examination on this point. So I am just simplify here some facts for the numerical calculation. If the question is asked in your examination, in the net JRF examination, I am describing here. After next class, I will discuss on the high energy compounds, and thereafter I will interact on some illustrations, and that illustrations will be important for your for the preparation of your JRF net examination. So I am just simplify here some facts. The fact is here that change in the energy in the biochemical reactions, in the chemical reactions, is equal to change in the extended internal energy, that is the delta G naught plus RT log E K E Q. And if we simplify here, because the KEQ represents the log value and the KEQ is represented in the form of log 0.01, only 3 or 4 you remember, nothing more. The 0. If the Q value is the KEQ value is the 0.01 value, 0.01, log means in the form of 10, log clearly represents in the form of 10. And if you remember that 10, the value of log value of 10 is 1, log value of 100 is 2, log value of 1000, that is 3, that is 10 multiplied by 10 multiplied by 10, 100, 10 multiplied by 10, 10 multiplied by 1. That means the log value of the 10 is 1, log value of the 100 is 2, log value of the 1000 is 3. Likely, the log value of 1 is 0. The log value of 1 is 0. The log value of 0.1 is -1. The log value of 0.01 is -2. The log value of 0.001 is -3. It is very simple. And here, if you calculated the change in the energy, just I am saying that I am simplifying here. At the log 0, the change of energy is 0. If you consider the log value at the standard, just I am D0 means that is the standard, and standard is considered at the temperature 25 degrees centigrade at 298 degree Kelvin. And here, if you consider, you just remember it. I am just saying for the remember or simplification of the calculation. And when the log K equilibrium value, matlab K equilibrium value log is 0, then the change in the energy, internal energy, that is gives free energy, is 0. If it is 10, that means the log K equation is 1. And here the change of energy is 1364 kilocalorie in minus. That means it is released. And if in 0.1, that here the log K equilibrium value is -1, and in this condition the value of the delta G0 is plus 1364. In one condition it is minus, in another condition it is plus. And likely if the value is 2, that means the change in the energy value is -2728. And if it is the 0.01, that is, it is very simple, -2728. These are the values sometimes asked in your question, examinations. So it is necessary to remember all these forms. And if we consider, the log value, then we again simplify it. That is the RT value. Just it represents the RT value, -2.3 RT value. It represents minus and plus. The value 1.364 represents the RT value. So you again simplify in the form of the log at a 25 degrees centigrade. If you consider it at 25 degrees centigrade, at the 25 degrees centigrade it is 1364 minus. So the change of energy at D0 naught, that is the standard change of energy at the constant temperature, the value is -1364 log K equilibrium. And when, because just I am saying that it will ask in the question sometimes, when only the reaction kinetics, the value of the reaction kinetics, that is the value of the molar value of the reactants and products are presented in your question, and energy level is demanded in the reply. And sometimes students feel very difficulty, sometimes students feel difficulty in the calculation in the classroom or during the examination. So it is necessary to remember the simplified form. And here the form at the, if it is mentioned in the standard value, if it is mentioned at the 25 degrees centigrade, so the equation is simplified here. That is, the dg naught is represented by -1364 log K equilibrium. So if you calculate the value of the equilibrium, rate constant of the equilibrium, then you easily calculate the energetics value. Second, sometimes the question is asked at the 37 degrees centigrade, or it is not mentioned the temperature, but it is mentioned that in the human being. And it is well known that the temperature of our body is 37 degrees centigrade, roughly 36 or 37 degrees centigrade. So in this condition, without the representing that the value is, what is the value of the temperature, it is understand properly that the temperature is at the 37 degrees centigrade. And sometimes students do wrong calculation. Why? Because here, if the temperature is changed in the condition of the man, the temperature is 37 degrees centigrade. And when the temperature is 37 degrees centigrade, the value of delta G naught is -1419 log. Then the equation is changed. And here, the simplified equation is change in the delta G equal to -1419 log K equilibrium. So it is necessary to remember this fact during the examination. Now, in last class, I said that in the biological system, pH has also role in the energetics. And in the biological system, the change in the standard energy is referred as delta G naught dash, not simply by the delta G naught. And it is considered that at this level, the pH is of 7. That is the neutral. And so, I am just explaining the fact that H plus ion appears as a substrate or product. Its standard state concentration is considered as 1 m, 1 molar value. That means we consider that the pH is at the standard value is 1 m, that is 1 molar value. And if we consider the 1 molar value, that means that it becomes the 0. When we consider the molar value is 1, H plus is 1, that means H plus ion, molar value of the H plus ion is 1, then the value of the pH becomes 0. Now it standardizes the calculation equation of the change in the Gibbs free energy. So, in this condition, the relationship between dG naught and the modified standard state of free energy, that is dG naught dash. dG naught dash means when we consider the pH at the standard level. That means at the pH 1 molar value, that means the 0. So, in this condition, the change in the dG naught, delta G naught dash, is equal to dG0 plus 1364 pH at 25 degrees centigrade. And in the condition of dG naught at the 37 degrees centigrade, the value becomes 1419. So, it is, as I suppose that you understand the kinetic relationship, the rate of energy. The next point which we are going to discuss today is the equilibrium constant. Just we are discussing that the equilibrium constant is represented that the ratio of the molar value of the products of products, multiplication value of the products, and molar value, just a minute. The K equilibrium represents that the ratio value of molar multiplication value of the molar products and molar value of the molar value of the substrate. Suppose the S1 and S2 are reactants and P1 and P2 are products. 2 reactants and 2 products. As for in the example, we observed in the C6H12O6 plus 6O2 produces CO2 plus H2O. That means here the two products and two reactants. The reactants are glucose and oxygen, and the products are carbon dioxide and water. Likely, if we consider the two reactants, that means the reactants is represented by S1, that is substrate 1, and substrate 2, and the products are represented by P1 and P2. Now we consider that the molar value of the reactants are A and B, and the molar value of the products are C and D. That is the concentration. Molar value represents the concentration of the reactants and concentration of the products. Then K equilibrium is represented by P1 in big bracket of the molar value C, P2 of the molar value D in big bracket, divided by S1 in bracket molar value A and S2 in big bracket molar value B. In this condition, the products are ratio of the product value of substrate, products to substrate represent the value of equilibrium, kinetics at equilibrium, that is K equilibrium. And here, if we consider the substrate, then the substrate has the two components, and if we the substrate represent the different natures, that change in the internal free energy is equivalent to the change in the internal energy of all substrates. Likely, if the K equilibrium, you consider the K equilibrium, then K equilibrium is for the substrate 1, product 1, and substrate 1, 2, and product 2. So it represents the summation value of each components of the reactants and each components of the products. Again, we calculate here the two other components from the value of K equilibrium or rate of reaction, that is K1, K2, like this. And the these components, that is energetics, and the energetic level is associated with the association and dissociation of the reactants and products or ligands. So here the standard free energy is also related with the association of two components or the dissociation of two components. Two components, that means the two biochemical components. And that factors are referred as dissociation constant and binding or association constant. Dissociation constant is symbolically represented by Kd. It is very simple. D for the dissociation. That means the dissociation constant is represented symbolically by Kd, and association constant is symbolically represented by Ka. That is the association. A for association, D for dissociation. That means Ka represents the constant, association constant, and Kd represents the dissociation constant. Now, if we analyze the reaction of the biochemical molecules, then the substrate 1 has the receptor and substrate 2 is ligand. So at the first, receptor ligand complex is formed, and the forward reaction, that is the attachment of the receptor and ligand to formation of the receptor and ligand complex, is if represented by rate A, and that is the association. If you consider the backward reaction, then it is the forward reaction, that is responsible for the association. If we consider the backward reaction, that means RL complex is dissociated to receptor and ligand, that is represented by B. That means the association is represented by A and dissociation is represented by B. And here the molar value of the receptor and substrate, molar values of the receptor and substrates are equal. That is 1 m of the receptor and 1 m is of ligand. And in this condition, it is very clear, in the forward reaction, that is, forward reaction means the association. Forward reaction means association of the receptor and ligand. That means it represents the Ka. That represents the Ka. That means here the product is RL. That is RL complex. Then the molar value of the RL complex with respect to the time or at the equilibrium is divided by molar product value of the molar concentration of receptor and molar concentration of ligand. This value represents Ka. That means when the Ka value is more and more, it represents the more and more binding capacity of the receptor. That determines the character of receptor. Because the binding capacity is more and Kn value is more. In another way, if we want to determine the Kd value, that is the dissociation value. And here, the RL complex, here we consider the backward reaction. That means the RL complex is dissociated to form a receptor and ligand. Then, here, the reactant is RL complex and product is receptor and ligand. That means the molar value of the receptor multiplied by molar value of the ligand divided by molar value of the receptor ligand complex. Then this value represents the Kd. This value represents the Kd. That means Kd represents more dissociation. More and more value of the Kd represents more and more dissociation. And sometimes in your JRF net examinations, questions are asked on the Ka and Kd. Again here, if we consider the relationship with respect to energetics and thermodynamics, both. You remember, it is necessary to remember, and if you go through the my previous live YouTube classes, then the change in energy in the form of thermodynamics, that is the delta G naught, is equal to delta H minus T delta S. That is the relationship I was described in both day. That is the relationship among the free energy, enthalpy and entropy. The second one is the change in the internal energy, which I was described last day and today. If we observe the change in the internal energy or Gibbs internal free energy, that is minus 2.303 RT log K equilibrium. Then in one way thermodynamics value is the delta H minus T delta S, that is the thermodynamic relationship. It is equal to the change in the free energy. If you consider the rate of reaction, then minus 2.303 RT log K equilibrium, it is also associated with the change in the internal free Gibbs free energy. Now we write both. That means the minus RT log K equilibrium, kinetics at equilibrium, minus RT log kinetic equilibrium equal to change in enthalpy minus T multiplied by change in entropy. That means symbolically minus RT log K equilibrium equal to delta H minus T delta S. And if we equalize, that means RT log K kinetic equilibrium equal to minus delta H plus T delta S. Then if we again equalize or normalize the relationship, then log K equilibrium equal to minus T plus T delta S divided by RT. That is the relationship between energetics and kinetics. Again, I am saying that log K equilibrium equal to minus change in the enthalpy plus temperature multiplied by change in the enthalpy divided by gas constant R and temperature T. Here again we normalize because the T is at the both side. Then we observe log K equilibrium equal to minus delta H divided by RT plus T delta S divided by RT. Again, if we equalize or normalize the equation, then log K equilibrium equal to minus H divided by R multiplied by 1 by T plus delta S by R. In this way, we obtain a equational relationship, quadratic equational relationship. That means log K equilibrium is considered as Y minus H divided by I considered as M, and 1 by T divided as X, and plus E that is the delta S divided by R. And in this way, if you consider and make a graph, then it forms a normalized value where y represent y-axis, m represent the slope of line, x represent x-axis, and intercept represent c. And if we normalize this form, it represents the rate of constant, because rate of constant is constant. It is a value of constant value. So in this way, we can able to draw a graph, and we can able to calculate the energetics with respect to the changes in the rate of reactions, or at the different rate of reactions, or at the different concentration of the reactant and molecules. We can easily calculate the value of free energy, we can easily calculate the value of enthalpy, and we can easily calculate the value of entropy. In this way, the topic is, we are discussing the all aspects here. The what is enthalpy, what is entropy, what is the free energy, how we calculate the free energy, what is the standard energy, what is difference between the D0 and D0 naught, what is the effect of the H, what is the differences between the physico-chemical thermodynamics and the thermodynamics of the living system. And not at the MSc level. Of course, in the some universities question is asked, but not commonly asked in the numericals are commonly asked in the MSc examinations. But in the NET examinations or in the JRF NET, frequently the questions are asked on the rate of reactions and energetics kinetics. So we are, I am going to close today class, and it is my kind request to must go through some previous books, previous questions asked in the JRF NET examinations. And if you find any questions related with the kinetics and related with the thermodynamic aspects, you must try to calculate the value and find the answer. And if you will feel any problem, then you will keep the questions for the my third class from today.